So this is the last in the series of AS Chemistry Unit 2. So Unit 2 is using analysis. There's 3 types of analysis that you need to know. I'm going to run through them quite quickly, but practice with these is going to make perfect in terms of how you use them. So the first one is mass spec. This is used to identify different isotopes and to find the relative atomic mass of each element. So in the other unit, you do Unit 1, you go into this in quite a little bit more detail, but there's like 5 steps to using a mass spec. So the first one is to ionize. A sample of element is vaporized and injected into a mass spectrometer where a high voltage is passed over the chamber. The removal of the atoms are ionized, leaving them with positive charges. Okay, then they are accelerated towards a negatively charged plate by here. And then the ions kind of drift and move because of a magnetic field, and they cause them to curve, okay? And then they have different radiuses depending on how large and how big a charge they have. They then hit this thing called a detection plate. At the detection plate, they will gain an electron from the flow of charge. The greater the abundance, the greater the current produced, okay? And then what we do is we analyze these to work out relative abundance of isotopes. So here's 2 different isotopes. You've got an isotope that's got a mass of 10 and an isotope that's got a mass of 12. So 75% when they passed it through came out as a mass of 10 and 25% came out as a mass of 12. And we can work out the exact relative atomic mass by putting it into this equation. Moving on then to infrared. Infrared, you'll get given all the data, so it's a little bit easier to use. So it's an analytic technique again to determine functional groups, different functional groups in organic compounds. So infrared radiation is passed through a sample where different bonds absorb the radiation at different amounts. The varying amounts of what they absorb is measured and recorded, allowing certain bonds and therefore functional groups to be identified. And you end up with these things called characteristic waves, and you'll get given a book to identify all the different, like the wavelengths, to identify all the different characteristic waves. So this is just looking at ethanol. The functional group of ethanol is OH, hydroxy group, and that's where it was absorbed. So there's the region of it being absorbed. With infrared spectrometry, you get something called a fingerprint region. So a region that's quite hard to read. There's lots of peaks very close together. This region appears due to tiny differences in a species and is known as a fingerprint, molecule's fingerprint. It's very difficult to interpret, so therefore will not be needed at A level. It's kind of this area over here, lower wavelength numbers, and it's all normally quite peaked, so you can't really read it. And then the final technique you have to use is MMR, which determines the structure of a molecule using energy of bond environment. So different bond environments within a molecule absorb different amounts of energy as they show different peaks. So there's all different types of MMR. So you've got hydrogen MMR, which shows different hydrogen environments, and you can see by here that they've colour-coded them. So samples are analysed and dissolved in a non-hydrogen containing solvent, so a liquid that doesn't contain hydrogen, so it doesn't produce any extra peaks on the spectrum. Normally carbon chloride is used. Okay. Hydrogen MMR spectra are more complex than the carbon-13, which I'll do in a minute, as the heights of peak show the relative intensity of each chemical shift. So we're looking at different ones. So this one here, 1, 2, 3. This one here hasn't got any other hydrogen surrounding it, that's why it's 1 peak. And this one here, it's got 3 hydrogens, okay? And then how you work out how many hydrogens are on the next carbon along is you look at how much the peak is. So if it's a singlet peak, there's no hydrogens next to it. If it's a doublet peak, there'll be hydrogens, 1 hydrogen either side. And then if it's a triplet, there'll be 2 hydrogens either side. And then carbon MMR is a little bit easier, okay? Different environments are shown as peaks with different values. Carbon environments are near to an oxygen, so the values are shifted. This is because oxygen is very electronegative and it acts to pull electrons away from the carbon atom. So you can see here there's one that's a CH2, one that's just carbons. So carbons would mean that they're attached to oxygens or something that isn't a hydrogen.